Okay, so thanks everyone for coming. And today's speaker is Anthony Kiely from UCD. Anthony's been working at UCD for the last 4 or 5 years, and now he's moving to Cork on a pathway fellowship. So he's leaving very soon. So we're glad to have him here before he leaves. And he's going to tell us about quantum control. So over to you, Anthony.
Cheers. Thanks, Shane. So I'm based in UCD at the moment. I'm moving to Cork next month, working a little bit kind of in quantum control, but also kind of continuous measurement. So today, I'm going to tell you a bit about the results in this paper from last year in PRL, and kind of just to sketch out the kind of idea to kind of have in the back of your mind. It's kind of in this kind of cartoon here. So the rough idea, and we'll get into the details of this, is you have some sort of initial quantum state, and you want to drive your system to some sort of target quantum state. And let's suppose you have some sort of way of doing that. You engineer your system in such a way that it goes from your initial state to the target state that you want. So your quantum system does what you want it to do, and you follow this kind of blue curve. So you kind of follow this kind of blue trajectory, and then because quantum systems are fragile, like you have some kind of errors, you have some kind of some kind of things you haven't characterized, and you're actually not following this blue trajectory. You're following some kind of red trajectory. How can you kind of ensure that, whatever kind of red trajectory that you're on, you still kind of end up close to your target state within some kind of error tolerance? So that's a kind of cartoony picture of kind of what we're going to talk about, but we'll kind of get into the details. Let's see if this works. Maybe not. Yeah, I can't even. Okay. Thanks. Okay, so to kind of zoom out a little bit, so what is kind of quantum control? So I like this kind of quote, control turns science into technology. So there's all these nice kind of quantum systems. There's trapped ions, there's superconducting qubits, and there's one thing about kind of realizing them in the lab, which is kind of a challenge in itself. But there's another thing about getting them to behave the way you want them to behave. So you could just let them kind of freely evolve, and they start in some sort of initial state, and they'd evolve in some way to some other kind of state, but you actually want them to do things. You want them to behave in a certain way. And how do you do that? Well, you have to kind of consider that there's some sort of state of interactions or kind of always on interactions. So say in the case of trapped ions, they have, Coulomb interaction between them. That's just there, and you're kind of not going to turn it off. And then on top of that, there's some sort of applied external field, so some electromagnetic field that you can apply in time. So the whole kind of idea of quantum control is, okay, thinking about these two parts, in particular the kind of time-dependent field that you apply, how can you use this to kind of drive the system to where you want it to go? So starting from some initial state, moving it towards final state, or even implementing kind of gains with these kind of things. So that's the kind of idea behind quantum control. But like I said, okay, there's all sorts of errors, there's all sorts of things that can go wrong. So, the frequency that you drive at could be wrong, so there could be some kind of detuning, so you could be off resonance. So then you kind of don't excite your atom the way you want to, or you don't kind of get the right kind of state transfer. You could have some kind of misalignment of fields. So if you think about your laser beam on an atom that has some sort of Gaussian profile, maybe these aren't kind of lined up, and the intensity that you think your atom sees is not the intensity that it actually sees. So there's kind of a mismatch between your theoretical model and what's actually happening in the lab. There's kind of leakage. So there's kind of leakages in the kind of atomic transitions. This is in kind of superconducting transmon qubits. So normally they work in these two lowest levels. So this kind of harmonic oscillator, that's kind of your qubit. But there's all these other levels, and they don't want them to live there. So you could leak into these other levels, and that's something kind of unwanted. That's another thing you don't want. There's kind of stochastic parameter fluctuations. So kind of parameters could vary from run to run of your experiment. You don't really understand why. And there's also kind of interactions with the environment or kind of that. So this thing for things like dephasing or other kind of effects. So there's lots and lots of ways which things could kind of go wrong. So maybe kind of as a warm-up, I'm just going to talk about this kind of old paper of mine about leakage, just to kind of build up a little bit of an idea about how you kind of counteract these. And then we'll talk about kind of more recent work about how you kind of correct kind of any kind of error.
What was the Meow et al. Paper that you were saying they were dealing with what system?
Transmon qubits. Transmon qubits, so superconducting transmon qubits. So basically, it more or less looks like, so yeah, it looks like a harmonic oscillator, which is kind of deformed. And the reason it's deformed is because if you had a harmonic oscillator, if you address these two levels, everything would be on resonance because all the spacing is equal. They want to kind of address this and not address everything else. So then they kind of warp it. And yeah, the transmon, what transmon means is basically it's a particular parameter regime of kind of how anharmonic it is, more or less. Yeah. Okay. Okay, so these are not the types of errors, but we'll just talk about kind of leakage error. So just to kind of give ourselves kind of an example task. So here you want to go from this state here to state 1 to state 2. So you can imagine these are kind of atomic positions. So you want to go from state 1 to state 2 in the presence of some kind of leakage. So in this case, okay, to discuss it here, you could have some kind of polarization error. This is like a atomic transition. So you could be trying to address this transition, but the polarization isn't quite right. So you're also addressing this transition, and this coupling, this kind of time-dependent field, is some kind of small multiple of the one addressing the correct kind of transition. And so what does this look like? So there's some kind of qubit Hamiltonian, which is this guy, so it's these two levels. And then there's this other part, so it's connecting into this level that you don't call it. So this is kind of our kind of example task. How do you get from here to here and not end up in this state? And to kind of start with, we should just think about, okay, how would we do this part? How would we just kind of control this two-level system if you had no leakage? So if, let's say, this beta, this kind of small number, if this is 0. So if you had no coupling to this, if you had kind of perfect polarization, how would you get from state 1 to state 2? Okay, so this uses what's called Lewis-Riesenfeld invariance. So this is kind of motivated by this adiabatic theorem. So adiabatic theorem says basically if your Hamiltonian changes very slowly in time, your state kind of follows the instantaneous energy eigenstates, you know, if it kind of goes slowly. And these Lewis-Riesenfeld invariants and these kind of Hermitian operators phi, they fulfill this kind of equation. And the idea is that the eigenvectors of this operator are kind of up to some phase solutions of the time-dependent Schrödinger equation. So this is kind of exact for any kind of finite time. You're kind of following the eigenvectors of this operator I. So it's this sort of analogy. When it's very slow, you're following the eigenstates of the Hamiltonian. At finite time, you're just following the eigenstates of this kind of operator I. And okay, why is that useful? We'll see in a minute, but the idea is that you want to go backwards. So normally you say, this is what happens. This is the time-dependent Hamiltonian. And then I solve my Schrödinger equation. I solve this differential equation, and I get how the state varies. So that's like the normal kind of problem. But this kind of allows you to go the other way around, that you basically specify, I want some kind of state evolution, want the state to do this. And then kind of using this equation, you kind of go backwards and say, okay, given that the state did this, what should the time-dependent Hamiltonian be? So you're doing kind of the reverse problem. And okay, I mentioned here, you normally want to start and end in some energy eigenstate, so you have some kind of boundary conditions, these kind of operatives. So this is, okay, maybe a bit kind of abstract, so maybe we'll do this for a kind of specific example, for a kind of two-level example. So this was the bit in the red box, so this is just the two-level system, so there's no kind of leakage now. And you can write down what is this kind of invariant operator. So this is more or less the most kind of general 2x2 Hermitian matrix you could write down. If you look at eigenvectors of this, you know, some kind of particular solution of the Schrödinger equation looks like this kind of phase. And then you can see, okay, the theta is kind of like the polar direction in your Bloch sphere, and the alpha is like your kind of azimuthal direction in the Bloch sphere. And so this kind of basically parameterizes your state, more or less, these kind of these angles. And if you put, okay, the h and the I into this equation, you get out basically a parameterized version of your Schrödinger equation. So some kind of time derivative of something to do with your state is, okay, this stuff. And you could solve it like a differential equation. Given some Hamiltonian, you solve this, and you get how the state develops. But you want to go the other way around. You want to.
You're just going to look for one state rather than two states from system.
Yeah, in this case, it's just enough to consider this one particular solution. But in more complicated settings, you might need to look at some linear combination of particular solutions. That's true. Yeah. Right. So the idea is you say, I want this state to evolve in a certain way. So it starts in this state, it goes to this target state, and it follows some particular path. And I specify this. And now I want to go backwards and say, what time-dependent Hamiltonian gives me that evolution? So I can just kind of invert this. So I solve for all the components of my time-dependent Hamiltonian. And now I'm not like doing any like differential equation solving. I'm just rearranging. So everything over here just depends on the path, state space. It just depends on these angles. And I just plug in what was the path, and then it comes out, what time-dependent, parameters should I use? Okay, so in principle, you could do any kind of, you could work out any kind of path and get the Hamiltonian here. And that's fine. So we can do the case if there's no leakage, but now we have some kind of error. So how do we use this to kind of correct for some error? And the idea is, okay, there's lots of paths from A to B, but some of those paths are robust and some of them aren't. So you're trying to think about which are the robust paths and which are the kind of non-robust paths and picking their kind of best. Okay, so this is what we want. So this is the probability that I end up in state 2 at a final time t. So this is what the thing that we want to be 1. So at the final time t, we want the probability that we're in state 2 is 1. And if we have some kind of leakage, if we have some kind of weak leakage, we can say, okay, this is approximately perfect. So it's approximately 1, because we did all this Lewis-Riesenfeld business, up to some kind of second order correction in our small problem in beta. So there's some kind of correction, there's some kind of weak error because we kind of leak into this third state. And we can write down what this correction is. So this is, you could call it a sensitivity or kind of some sort of susceptibility. And it's basically like an integral over some stuff, which basically depends on the path. So depending on the path, you get different kind of sensitivities. So some paths are more sensitive and some paths are less sensitive. And the way you quantify this is exactly this number. So the smaller this is, the less sensitive the whole protocol is, and the less like leakage you will get. So I'm plotting here this sensitivity measure, so this Q, against the detuning. If I go back maybe. So this detuning, so how far the levels are separated times the time. Okay, so you can kind of see that, but you can actually show a little bit, like if there's no detuning, if the levels are like on resonance, it doesn't matter what you do. You get some kind of constant and you kind of can't correct for it, which makes sense. But other than that, if you have some kind of small detuning, you could correct for it. You can also show some kind of lower bound for this. So you can show this lower bound, which is this kind of dashed black line. So basically, for a given detuning, you need a certain amount of time, at least, to really kind of correct for this kind of error. And then what you could do is you could check different kind of protocols. This red one, this is kind of a flat pi pulse. So this is a classic kind of case of basically you have constant field intensity. So you turn it on, you wait for the right amount of time, and then you turn it off. So it's kind of the simplest thing you can do. This, okay, turns out isn't very good. But you can do some kind of numerical optimization about picking what is the kind of correct path. And this is this kind of thick kind of green line. And you can see, okay, as a benchmark, it's quite close to the kind of lower bound of the best you could possibly do. So you could really kind of eliminate these kind of leakage errors as much as you kind of possibly. Okay, so that's good, but this is kind of some approximation. This is some kind of, Taylor series kind of perturbation theory thing. And you could check, okay, if I did make this 0, does that actually correspond to it working? So you could go back and you could simulate the full kind of 3-level Hamiltonian and check, does this kind of numerical optimized kind of protocol really work? Does it do the job? So that's kind of what's shown here. So here's some kind of messy optimized pulses. They don't really matter so much. But on the left here, this is the probability I'm in state 2 as a function of how strong the error is. And okay, there's lots of different protocols, but the one you want is just the blue one, it's kind of the optimized one. And here we're kind of at the boundary of kind of our lower bound. So here it's flat, it's much better than the other one. It's not perfectly flat, so it has some kind of second derivative. But if you have long enough time, you can really kill this term. And so the second order term is 0, and it's really just very, very insensitive to this error. So even if you have kind of strong leakage errors, you still end up with your population in state 2. So you're kind of correct. So that was kind of like our warm-up example. So that's kind of like, how you do correct for a particular kind of error. It's kind of the image. Okay, so what I want to talk about now is just kind of, robust control in a kind of more general sense. Okay, so yeah, kind of zooming out a bit, we had a kind of a time-dependent Hamiltonian. There was some kind of ideal Hamiltonian, which is, that's what we think describes our model. And there's some kind of weak perturbation. And okay, kind of going forward now, we're just going to assume this is static. So this is just some sort of time-dependent perturbation. And kind of like in the diagram before, you somehow engineer this numerically using some analytical tricks, whatever way you want, to have this optimal blue path, so you hit the kind of target state, or in this case, kind of target unitary. But if you have this perturbation, it pushes you off somehow. Depending on how strong it is, you kind of end up. And there's kind of two approximations you can make. One is, that this is weak, so you can kind of series expand the fidelity, so it's the gate fidelity now. So it's approximately perfect plus some second order corrections. So this lambda now was the beta from before, so it's some small parameter. And you have this kind of fidelity or gate susceptibility, which is this thing. So this is, so it just depends on the norm of this V0 bar operator. So this is basically this V in the interaction picture with respect to this guy. So that's what this is 0. And there's a bar because it's time averaged. So it's V in the interaction picture time averaged. So given what V is, what this kind of susceptibility is, and you can write this. And so lots of people have kind of played this game that I showed you. So this is another paper. They want this kind of flat line with error. This is another case. Again, this is fidelity against kind of error. They want this kind of flat line. This was this nice recent experiment. They're doing this kind of same business in spin qubits and silicon. So this is in John Nichols' group in Rochester. Okay, so this is kind of well understood. So how does my stuff come into this? So basically what I want to do is I want to kill this kind of second approximation. So I just want to say, I have some weak error, and I don't know what it is. So there's some V, but I don't really want to get into the specifics of what it is. So I just have some kind of weak error. In this case, okay, it's static. So I have some kind of weak static error, whatever it might be. How do I correct for that? How do I kind of compensate? So that's kind of our question. And this is the kind of recipe we came up with. So this is what we're calling kind of universally robust quantum control. So you want to kind of find a control which is robust to any kind of weak error. So there's kind of 3 steps. So the first step is I'm going to write all my operators as kind of vectors. So I'm going to use this kind of curly kind of cache notation. So there's lots of ways you could do this. You could just kind of take the columns and kind of stack them. But basically, you represent your any kind of operator or matrix as a vector. And then our susceptibility, thing that's important is this V0 bar. And you can find out that this is actually a linear operation, so on V. So you can define some kind of superoperator M0, which takes V the vector now, to this V0 bar. And this is the thing that you're interested in. And this susceptibility is the norm of this business. So if you were to minimize the norm of this M0 thing, regardless of what V is, your susceptibility would be very small. So it's not super complicated in a way. So if you were kind of to minimize this, it's kind of like a susceptibility for any kind of V, regardless of what kind of V that you have. Okay. Okay, so this is some kind of technical bits, which maybe I won't dwell on too much, but this is what I was talking about. So this is M0, which basically takes some operator, you put it in the interaction picture, and then you time average. This is how you would do this. Well, it's one way you can kind of vectorize things. So you basically want to rewrite some kind of matrix as a vector. There's lots of ways you could do this, but in this particular mapping, then your kind of superoperator looks like this. So this is one way of kind of writing it. And it turns out this is, okay, this is some kind of nice properties. One thing you might notice is that the identity is some eigenvalue or eigenvector of this thing, kind of eigenvalue 1, which basically means that if you had a V, if you had an error, which is just identity, it's just some energy shift, which you kind of can't correct for. Like it doesn't really have any effect anyway. But so like V is the identity matrix, not so kind of important. So sometimes you might see I have this tilde, which basically means I've project it out this kind of operator. And in fact, if you have any kind of conserved quantity, this is also an eigenvector of this kind of superoperator thing with constant eigenvalue, meaning if you have a conserved quantity, you can't really correct for it, which also kind of makes sense. And everything I was talking about was for gate fidelities. You can also do this for states, so just kind of state evolution. And there, instead of the norm of V0 bar, you just get the variance of V0 bar with respect to that initial state. So you can do the same thing for states, and it kind of goes through the state. Okay, so that was kind of a little bit kind of the technical details if you want to know about that. But okay, back to kind of the main story. So we're going to kind of compare 3 different cases now. So the first case is going to be in gray, and the only thing I'm going to do is I'm going to make sure that, in the absence of any kind of error, I hit my target gate or target state. So if there's no error, it does the job. So that's the only thing I'm going to optimize for in the kind of gray kind lines in the plots. In the blue lines, I'm going to do what we were doing in the kind of leakage case. So I'm going to optimize that if there's no error, it does the job. And also, if there's some particular error V that I know about, it also is robust to second order. And then the orange lines, I want to do this kind of new method that we're talking about. That okay, if there's no error, it works. But also, if there's any possible error, so minimizing the norm of this 0 business, if there's any error, it's also kind of 0. And one thing which I maybe didn't kind of dwell on is, in all this kind of optimization, you just have to simulate the kind of error-free dynamics. So kind of in the leakage case, I didn't really need to understand the details of the full 3-level system. I just needed to do all this Lewis-Friesenfeld business on just the qubit, just the simple system. Okay, so how do these kind of stack up? Yeah.
Why did you have an X on the JV in the last one?
An X on the...
You crossed out the JV on the last line. What do you mean by that?
Oh, sorry, right. Is it
not a form of JU? So
yeah. Just in the sense that I'm not in the numerical optimization, I'm just minimizing this kind of cost function and this cost function, and I'm not thinking about that. But yeah, it is true that.
Is it not gone as well?
Yeah, it is gone as well. That's true. Yeah. So that would be automatically, if you were to calculate it, it would automatically be 0. That's true. Okay, so these are the 3 cases. So kind of gray, blue, and orange. And this is kind of, a really simple example again. So this is just some qubit where the time-dependent control is basically what axis you're kind of rotating around. And you try and optimize these things. And the first thing you notice is, okay, there's some kind of hierarchy of time scales. So you're trying to minimize these cost functions. And if you're just trying to get it to hit the target state, you need at least, in some kind of units, at least a time of 1 to really kind of hit your target gate in this case. And then if you demand, some robustness, if you demand that it's robust to kind of some kind of sigma z error, this kind of time increases, so now it's kind of 2, so you need a longer time. And then if you demand more, again, that it's robust to basically any possible V, any kind of possible error, it goes up to about kind of 2.5. Okay, so there's some kind of quantum speed limit effect here, but the takeaway, I guess, from this is you can minimize all these things, so you can make them. And now, just like in the leakage case, you can go back and check and simulate the full setting and see, okay, does minimizing these cost functions, does it do anything? Does it actually work? So that's kind of what's shown here. This is the same kind of process before. So this is the gate fidelity against some kind of error. And here the error is sigma z. So in the gray line, it does what you expect. It's 1 when there's no error, and otherwise, okay, it drops off quite quickly. But the blue and the orange ones are kind of flat, because the blue one is specifically for sigma z. And over here, I basically averaged over lots and lots of different V's. And okay, some of them might be near sigma z, so the blue line is a bit better than the gray line. The key thing is that the orange one is still very flat with respect to the error. So kind of whatever kind of unknown error that you have, whatever it might be, it somehow kind of cancels it out. And okay, these are the kind of complicated field profiles. This is kind of some kind of piecewise constant thing, but in principle, you could use any kind of basis.
So in these graphs, what have you actually done here? You're taking a 3-level system
So in this case, it's this two-level system
The two-level, which is perturbed
with any like all sorts of random V's.
there are three, just one additional level.
In this case, not actually any additional levels. This is still just like this is 2 by 2 and it's 2 by 2 kind of error.
Or is it for two-way two perturbation?
Yes, yeah. So all sorts of kind of random ones, and then you calculate that for different values of, let's say, lambda.
Okay.
So the so that's what's on the x-axis, how strong the strength of this is, and then you calculate, basically the gauge fidelity.
Yeah, no, it was just that I hadn't understood there was a perturbation with a 2 by 2.
Right. Yeah. So we'll look at other cases, but in the moment it's just 2 by 2. Yeah. Okay. So the takeaway from this is it works. It seems to do what it's supposed to do. Okay. This is maybe a little bit technical again. This is just thinking about how you would optimize these things. You could kind of combine these class functions together. This is what we do in that case. You can also do some sort of constraint optimization where you optimize the fidelity to 0 error first below some sort of threshold value. And once that works, you optimize this kind of second class function with some sort of constraint that the fidelity with kind of 0 error never gets above some kind of value. So there's lots of different approaches. You can also do some kind of gradient-based things. But maybe I won't go on the kind of numerics. This is a little bit what I was talking about if you have some sort of threshold. So this is green circle from before. So depending on this threshold, does this affect how robust you can get it? It turns out, this actually isn't the case. So regardless of how kind of tight you draw this circle, you can still make this kind of robust function. More or less 0. Doesn't seem to. Maybe a more interesting question is, how does this work? Like, why is this working? Because it seems a little bit too good. So basically, any possible V, it kills to second order. So what are you actually kind of demanding? So you're basically demanding like this superoperator, if it acts on some V, it more or less gives you 0. So if you do this, interaction picture, then time averaging, it more or less washes out any information about V, and you get back something which is just kind of proportional to the density. So it sort of washes out any kind of V effect. And this kind of relation, this is kind of known. So this is the same effect that you would get if you did what's called a Haar average over the U's. So what is a Haar average? So if you had a uniform distribution of unitary matrices, and you kind of were integrating over that uniform distribution, this is what's called doing a Haar average. So it's kind of, the way I would think about it is kind of like in this kind of figure here, like if you're thinking about it as a sphere, it's like points uniformly distributed over the sphere, like one way.
You're projecting onto the singlet V. So the singlet part of V will survive.
You mean this part, or?
Well, in your Haar average, your Haar average is a projection onto the singlet. So if V is proportional to the identity, then you just get V back.
Yeah, that's true. Yeah, if you
It's a standard projection onto the identity in group theory.
Okay. Right, but this is actually a weaker condition than just Haar averaging, because you only this would be true if you do a Haar average, but we all lots of things would be true if they were kind of, the U's were kind of Haar distributed, but we just want this condition, which is basically we only want the second order term to vanish. Maybe the higher order terms, would be involved with kind of other things that do.
If you're not actually integrating over the group, is what you're saying.
What you could think about, so you have all these U's, which are generated by the time evolution. And normally when you're thinking about this Haar average business, you're thinking about a discrete set of U's. A lot of kind of quantum information, they have a discrete set of U's. Here, it's a little bit different in that, you can think about it as a sort of, continuum, which is indexed by the time, and you're integrating over the time.
I see exactly what you're doing, but you're assuming that you've got some stochasticity in your evolution there, and that it's covering the group in some in some sort of way.
Yeah. So this is kind of getting to like, why does it work? So it's sort of, if you knew what the error was, you can do a sort of, it's known how to do these kind of back and forth evolutions, which sort of average out the error. Here, you don't know what V is, so you have to do a kind of even more convoluted, in some way, kind of state space evolution, where you're kind of doing this sort of windy path in such a way that if there was a perturbation, because you do this sort of uniform path, in some way it sort of averages out the V. That's the kind of rough intuition. Yeah, I don't know if that makes sense.
No, I mean, if you integrate over the group, you get it will kill it and project onto it, as you said. But if you don't integrate over the group, you're going to be left with some residues, and that requires for it to look like integrating over the group, the parameterized paths of views that you have there should average over the group. They should be dense in some natural sense on the group.
Right. Okay. Yeah. So in some way, this kind of Haar average thing is like, we didn't start with this. We just started with the kind of perturbative error, and this turns out to just, I don't know, be this nice kind of connection, that this is this kind of one design condition, which in some way makes sense, that it's doing this kind of weird evolution, and it also kind of fits with this kind of speed limit idea that you sort of need a longer time to somehow do this kind of windier path, kind of cancel things out.
In your numerics, for example,
Yeah.
Like you showed 1 minute ago, where you had all fields, one for where you have the Z perturbation, and the other one that worked arbitrary. But
Yeah.
looking at the picture, they seem kind of like one didn't look any more complex. And
No.
Well, it has to be, I suppose, because of this argument. It's like you need a much less complex path of the unitary.
Yeah, like I think it's kind of hard to see it from the control field, because in some way that you have to put that into the Hamiltonian and solve the Schrödinger equation, get out the unitary. So I think, yeah, like if you just look at the control field, they're all just some complicated mess. I don't think you could really see it from looking at it. I don't know, is there an argument for them that it'd be like more complicated?
I suspect you could see it in the example, because you were dealing with just SU2, and SU2 is just S3, so you can just see how well you are covering the tree sphere.
Yeah.
Just looking at what points in the tree sphere you're getting in each value of the paths.
Yeah, I guess the tricky thing is it's not like you can just put in the U's for free. Like you have to change the Hamiltonian in time in such a way that it would generate these U's. And yeah, then for certain Hamiltonians, you would have some sort of constraints that maybe you can't just generate whatever U's you want, or this kind of thing. But no, I think you're right. Like if that it is kind of in some way, like uniform over this kind of set. Okay. And this condition, this kind of one design condition, if you go through it, I'm going to get myself more trouble here, but if you look at the norm of this M0 thing and you kind of work through it, you get this kind of condition. So this is the time evolution curve, which takes you from S1 to S2. And this is exactly what's called its frame potential. So this is also kind of a happy accident. And this frame potential basically measures how close you are to a T design. So in some way, what we're doing is, as you minimize this, when this whole thing eventually becomes 0, this part becomes 0, and you get exactly back this kind of conditions where the point is. So it has this kind of nice linking, even if it's kind of a bit of a different. Right. So one other question that you could have is, this is fine if the system is small. If the system is very big, and you want to be robust to like all possible V's, if the system is big, there's a lot of different V's that you could be robust to. So this might in scale somewhere. So what you can do is basically the same as way that I kind of projected out the identity, because I kind of wasn't interested in that. You can basically design some kind of projectors over the kind of V's that you're not interested in. So you say, you know that maybe there's some kind of transitions that are just forbidden, or you couldn't have 3-body or 4-body errors because it's kind of physical. So you could basically kind of construct some sort of projector which projects out these V's, and then you get a new kind of N, which is the old one, but just these kind of terms kind of projected out, and you have a kind of a smaller superoperator, and you just have to minimize the norm of that. And so it's kind of an easier problem, and it's robust to kind of a smaller set of these V's. So you can do this kind of continuous interpolation between being robust to like a specific V, the specific error, and being robust to kind of every possible error, and all the kind of things in between. Okay, so this is kind of an example of this. So this is kind of a 2-qubit case. So these are the kind of same lines as before, apart from the green one is robust just to kind of single body operators. So if you have Sx, they're all flat apart from the gray one before. If they're kind of one body, so here the average over lots of one body V's, this blue one kind of drops off because this was designed specifically for Sx, specifically for this case. This kind of drops off now. And then over here, it's kind of average over like arbitrary V's, like any kind of possible V's. And now this green one also drops off because it was only designed for kind of single body V's. So you can kind of really see that this kind of behaves in the way that you do. Okay, so yeah, so that's kind of the summary of everything. So this was worked on with Ababaji, Gabriel Jakara, and Steve Campbell. This is the kind of paper. And basically the kind of takeaway is there's this kind of numerical method to basically design your control fields such that they're robust to any possible error, any kind of weak static error you can really correct for kind of dynamically in time. And there's a kind of nice connection with one design. There's also kind of open questions about this. There's this question about kind of speed limits. So kind of understanding a little bit, if you have these higher demands for robustness, how does this change like the minimum time that you need to kind of implement these things? There's also a question of the kind of limited control. So, you can show that if you have a very general Hamiltonian and you can generate all U's, you can always minimize this thing. But if you have some sort of fixed Hamiltonian with some kind of structure, and you can only do certain operations, this limits what kind of U's you can generate. And then this would limit, how small you could make this functional, and so how robust it could really be. So understanding a little bit of this connection would be nice. There's also ideas about kind of robust sensing. So in the way that you're kind of selectively robust, you could also be kind of selectively sensitive. So this susceptibility term I didn't mention, this is actually in the case of states, this is the Fisher information, if you're familiar with that. So you could make this term very large for one particular V. So you're very sensitive to changes in that particular V. And then using what I was describing with this projection technique, very robust to all other kind of errors. So there's this kind of selective sensitivity. Okay, so I think I'll leave it there and I'll take any questions you might have.
So you have this results that you don't actually need your sequence of unitaries to be Haar distributed. You just need one design.
Yeah.
To get the universal robustness. But if you did, instead of a one design, you had a two design, do you gain anything at all? You're robust to these type of errors that you're talking about. But, I'm just wondering what's the difference between the two.
Yeah, so the way they do the naming convention, like a two design is also by definition also a one design. And you would think then that would kill maybe the next order. At least that would be the intuition. I tried to work this out and it was a little bit messy, and so we kind of left it at the end. But yeah, the intuition would be higher order designs correspond to higher order susceptibilities in this kind of series expansion of the gate fidelity. But I don't know if it's like a one-to-one kind of correspondence.
If you're Haar distributed, then you expect most of all words.
I haven't proven that, but maybe, yeah, that would be kind of the intuition. Yeah, but maybe that's too demanding.
What happens if we try to break the database?
What do you mean, sir? The break.
So the change is happening very slowly. So
Right. In these cases, actually, no, it's not adiabatic. Yeah. It can be in arbitrary time. That's true. Yeah. So okay, maybe I confused things a little bit when I was talking about this adiabatic theorem, but this Lewis Riesenfeld stuff, the idea is that it's kind of analogous to the adiabatic theorem in that you're following the eigenstates of some operator, but it's not the Hamiltonian now, it's some other kind of operator. And in the adiabatic theorem, it's like an approximation, whereas with this Lewis Riesenfeld invariant business, it's exact, basically. So it's like a fixed thing for any time. It doesn't have any kind of condition associated. Yeah.
Lewis and Lewis Riesenfeld has nothing to do with the former professor of diastole potential.
I don't know, it could be, yeah.
No, it's
He
old
was
paper.
active in those type of things in the 60s, late 60s. I saw the reference.
Yeah, I think it's
What was
69.
but he didn't give his first initial.
Right. I think it's 69 was that paper.
And what was the initial of the person? And we can stop the recording.
Yeah.
But it could well be.
Right. Okay. I have no idea.
Where was the author at the time?
Thought they were in the US, but it's been a very
Oh,
long
it was in
time.
the US.
I think so, but it's been a very long time since I've looked it up.